synchronize. So I have a bit of a problem, or I had a problem. This thing I built cost so much money. It cost almost $300 to make, but I needed it. So the backstory is I had to go somewhere and I had to take a class, and it was 3 months long. So that's a lot of dust. I probably shouldn't breathe whatever this is. Probably should spray this table off. My point being, I needed to go away for 3 months, needed to water my plants. Well, I could ask someone nicely to do that for me, but it's easier to build a machine. So I built a machine. I built a watering machine that waters all of my plants. And it worked, sort of. Some plant, I actually just got back like 2 weeks ago, and a lot of the plants survived. Some doubled in size. Some did die because they got watered too much. It was that powerful. But now I'd like to describe how this complex machine did work. And it does exist. In fact, I'm sitting right next to it. You just can't see it. So I've rotated my camera slightly to this direction. As you can see, the spider plants have grown quite substantial. But I need to direct you, fortunately there's a little nub, down to the pit. So that looks gross because it is. But this water is in a basin. That's about 16 gallons on most of these systems. That water has inside of it a submersible pump connected to a pipe. This pipe heads upward to this bucket on top. So you'll see that there is a tube here. That's not the tube we're talking about. We're talking about this tube back here. That tube leads into the bucket. So in fact, I will turn it on because these plants need water anyway. So when the system is activated, water flows, where's my finger? Where's my finger? There's my finger. Water flows up and into this bucket. Now this bucket has two outputs. The lower output is back here behind it and connects to this. So what this is when the water fills up, it will flow down into this system when the bucket gets high enough. It will then distribute through these two valves into two different directions. Each of these connections comes down, goes through a little connector into these basins. You can see there's a bunch of Christmas cactus. Stop jumping. Bunch of Christmas cactuses. That will fill up eventually with water, and in turn flow out and down this into the next one. It'll fill up, flow down, out, and then all the way back down into, it sticks into this. So it's in the basin and flows back in. Now you ask yourself, well, how do I keep that from putting all the water up there and then having the water come down here? How am I going to regulate the flow? Is there a float valve? No. No. I'm not smart enough for a float valve. That's what that big, thick, girthy pipe is for. That's a 1-inch piece of pipe. That was $49 for the whole ream of it. And the ream was only like this big. So it goes into this big column and dumps back down. You notice it's at the top of the bucket. Ah, the water just started flowing. So there's a bit of leakage, but it doesn't really ultimately matter. When the bucket gets too full, not all the water comes out here. It goes up here and comes down and out here, flowing back down. Because it's so thick, the water can't possibly overflow the bucket. It'll all flow back down and out, as long as the seals remain valid. It's sealed with this stuff. I use like the whole thing of caulk. I use 2 of these. Massive amount of caulk. Huge caulk. Now, you'll also notice it does diverge here. So the divergence connects to another basin, which is full of those spider plants. And below it, another basin. Below that is just random junk and not focus. And it goes back to the basin. Now, you will note that I said there are 3 of these. That's why it was so expensive to make. There's 3, each with that dual system going to, it splits by the valves and goes to 2 columns. I will put a picture of the first one here. And a picture of the second one here. I'm going to leave it running because those plants kind of do need water, but the Christmas cactuses are blooming, so I have to hurry with 2 additional points. Firstly, Obviously, this thing can't run the entire time. It would flood the plants. They'd be constantly wet. And at that point, why don't I just pour water on the plants and then leave them soaking? The answer is plants can't tolerate that. If the roots are deprived of oxygen, they become depraved. And we can't really have that. That perversion of plant material just isn't allowable in this context. So I built a brain. Fortunately, it's a relatively simple brain. This is a brain. It's actually a complicated system of timers. So you can look in there. It's just a wire with a plug that leads to a switch so I can control it. Indicator light. I have a lot of them. And then there's a timer. This is a once-a-week timer. Turns on once a week. Anytime I program it to. It's digital. See, it's got a little screen. That in turn, well, because that's the thing, is I can turn this on for up to, as low as 1 hour. This thing takes, when it's fully active, about 2 hours to run. I can set it to run 2 hours any week, but then it'll be running every single week. The plants won't get a chance to dry out. It needs to be about once every 4 weeks. So in order to calibrate longer than a week period, because it's only a week-long timer, it connects to a timer over here. That timer is 1/4 of the time. So that means that this timer will make a full revolution once every 4 weeks, or it spins really slowly. So 24 hours, it'll need 4 24-hour periods to go all the way around, which is 4 weeks. This thing turns on for 24 hours, it turns 1/4 of that. So that would turn it on, that then activates this timer, which in turn, every once in those 4 periods, when it's on, will turn slowly, activating itself at a different point. I am not sure if the math actually maths on this, but it did work, so apparently I did something right. So basically it's designed by this combination mathematically to every 4 weeks be on for a period and activate this one. There's this light bulb. I put a light bulb on it as an indicator. The room lights up when the thing turns on. But this isn't the only thing I built for it. There is a second component. And the second component is that, well, I don't trust myself because I have that tendency to slowly... Gotta watch out for that. Electricity, gotta watch out for that too. This thing has a high probability of leakage, and leakage results in messes, especially when I'm not here for 3 months to keep an eye on it. So I built an emergency safety shutoff system. We can actually, at this point, see an example of the overflow. Notice the bucket is full. The bucket can't overflow because the water flows back down through this tube. That's why it's all foggy. It is a little leaky, but fortunately that's directly over the Christmas cactuses, so the water just goes over there. You can also see that it's starting to run where water is flowing about that deep right now. So it'll take a while before it gets deep enough to actually flow through the system. Okay, so I had to actually remember how this thing works because I had no idea. It's kind of crazy that it does. It's this thing specifically. It doesn't normally have the light. I put the light in there to demonstrate. Now, I don't like to be around this because I didn't have time to actually insulate it. So if you touch it, you'll get a big zap. But it does work. So, how it works, there's a reason I haven't plugged it in yet. It's a plug. This plug connects into the brain, which is now on the floor. So when the system turns on, this thing becomes active. This plug is just connected to this. So you'll notice there's a thing, that's a 5-volt power supply. That powers this internal circuitry. You don't connect anything to this. It runs through a relay to the other side. And by default, the relay is closed. So that allows electricity to flow directly to the other outlet, which means that when you plug it in and you don't touch anything dumb, the light turns on. It's green because I had it. The circuit has another element. I don't know how comprehensible this is. Pause the screen and take a look at it. Essentially, this is the side we're talking about. This side is always connected to the AC. It'll run by default, doesn't require any power. The coil in the relay is off. This isn't how you draw a relay, it's how I draw a relay. So I'm not an electrical engineer. I don't get paid the big dollars to do this. I stared in the green bulb and now I'm blind. I figured that was going to happen eventually. But anyway, relay doesn't run, nothing's happening. What does happen is that there's a transistor up here. It's bolted in right there. If the base of that transistor is connected to positive, it conducts. It amplifies. Only a little bit of resistance is required. It then It then puts that positive through the relay, activates the relay, which I'm imagining that pulls the switches down. So the switch moves, disconnects this. The whole system shuts down. But also, it connects the other side of it to, this is connected to positive, it's actually connected through a resistor, connects to the coil. So that means the coil is now stuck on. The transistor's bypassed, it's not doing anything anymore. It's not connected to anything. The relay is just feeding itself. So long as it remains energized, it'll stay that way and keep the circuit off. Since it's on a timer, at a certain point after its 2-hour cycle is done, the cycle passes, the whole thing turns off, the coil goes off, the relay resets, and it's ready to sense again. What does this mean in practice? This means that in practice, that transistor is connected by 2 sets of speaker wire, which is double braided wire through a translucent conductor. It used to be used for speakers back when people had sound systems back in the 80s. Connected to 2 of these devices. So this device is, I'll try not to touch the electric part, a pair of copper rods, a piece of spare concrete that holds them down on a paper towel. There's 2 of them, 1 under each rack. So that means there's 3 of these brains that are all connected to, or 3 of these sensors that are connected to the brains. Each sensor has 2 probes, because there's 2 racks per thing. So it works out mathematically. What happens is, if water, as is in this cap, is spilled on the paper towel, 1, the water flows toward me, it conducts. It conducts between those 2 things. Not enough to actually power the relay, but enough to trigger the transistor, and turns the system off. I can take that off, it can interrupt again, it's locked. It'll be forever locked as long as there's electricity applied to it. However, say this dried out. It's been 4 weeks, it's dried out again. The system resets itself. Goes off, oh, it's back on again. It turns on, more leakage, turns off. Neat, huh? It's stable enough that it can sit like that for days and it won't really have an effect. It's just running through the resistor and the coil, so it's not going to hurt itself. That means that if the system breaks, if there's flooding on the floor, it shuts off the system. Admittedly, anything that's in the system will come out on the floor, but it'll disperse and dry up rather than it draining the whole 16 gallons onto the floor. So, that ultimately means that it's safe-ish. I don't think these things actually activated, but they were a last-minute addition. I'm like, I don't trust this thing. With that in mind, the irrigation system irrigated. It worked. It supported the plant life. I consider it a success. It actually ran successfully, and that's not something I can say about most of these things. I don't know if it'll work long term, and I don't think I'll be using this thing that much in the future. In fact, there's another device I need to make that will make this vastly improved. It can use the existing infrastructure for something much more detail-oriented. But that's a topic for a future video. This one's done. The machine, by definition, worked because I'm not flooded.